Alright, let's continue. Okay. If I remember correctly, we are in a site like this one. The importance of unique. It is difficult to overstate the importance of unique in the history of operating system, influenced by earlier system, in particular the famous Multics system from MIT. Unix brought together many great ideas and made a system that was both simple and powerful. Underlying the original Bell Labs, Unix was the unifying principle of building small, powerful programs that could be connected together to form larger workflow. Okay, but simple and powerful. The original Bell Labs Unix was the unifying principle of building small, powerful programs that could be connected together to form a larger workflow. The shell, when you type command, provide primitives such as pipes to enable such meta-level programming, and thus it becomes easy to string together program to accomplish a bigger task. For example, to find length of a text file that have the word foo in them, and then to count how many such line exist, you would type grep foo file.txt, right? This is the pattern or the word that we want to search inside this file.txt, and then we give the output to the WC -L, the WC program. This one. And the -L means that print new line counts. So that is the concept of piping, as far as I understand. This is the pipe. So we give the output from previous comment as the input from the next comment. Thus, using grep and WC word count program to achieve your tasks. The unique environment was friendly for programmers and developers alike, also providing a compiler for the new C programming language, making it easy for programmers to write their own programs, as well as CRTM, made Unix enormously popular, and it probably helped a lot that the authors give out copies for free to anyone who asks, an early form of open source software. Making it easy for programmers to write. Okay. Also of critical importance was the accessibility and readability of the code, having a beautiful small kernel written in C, invite authors to play with the kernel, adding new and cool features. For example, the enterprising group at Berkeley, led by Bill Joy, made a wonderful distribution, the Berkeley Systems Distribution, or BSD, which has some advanced virtual memory, file system, and networking subsystem. They later co-founded Sun Microsystem. Okay. Unfortunately, the spread of Unix was slowed a bit as companies tried to assert ownership and profit from it. Okay. An unfortunate but common result of lawyers getting involved. Many companies had their own variants. Sun operating system, Sun OS, from Sun Microsystem, IX, is that the word? Is that how to pronounce it? From IBM, SPUX. Okay. From SP and IRIX, from SGAI. Okay. The legal wrangling among AT&T/Bell Labs and this other player caused a drag out over Unix, and many wonder if it would survive, especially as Windows was introduced and took over most of the PC market. Okay, another side, and then came Linux. Fortunately for Unix, a young Finnish hacker named Linus Torvald, I'm not sure how to pronounce this, decided to write his own version of Unix, which borrowed heavily on the principle and ideas behind the original system, but not from the code base, thus avoiding issues of legality. Okay. He enlists help from many authors around the world to advantage of the sophisticated GNU tools that already existed and soon Linux was born, as well as the modern open source software movement. As the internet era came into place, most companies such as Google, Amazon, Facebook, and others chose to run Linux as it was free and could be readily modified to suit their needs. Indeed, it is hard to imagine the success of these new companies had such a system not exist. As smartphone became a dominant user-facing platform, Linux found a stronghold there too via Android. For many of the same reasons, and Steve Jobs took his Unix-based next step operating environment with him to Apple, thus making Unix popular on desktop. Though many users of Apple technology are probably not even aware of this fact, thus Unix lives on, more important today than ever before. The computing gods, if you believe in them, should be thanked for this wonderful outcome. Alright, let's read the summary. Wait, I kind of forgot to bring out this, the table of content. Okay, we're currently in summary. Thus, we have an introduction to the operating system. Today's operating system makes system relatively easy to use, and virtually all operating system you use today have been influenced by the developments we will discuss throughout the book. Unfortunately, due to time constraints, there are a number of parts of the operating system we won't cover in the book. For example, there is a lot of networking code in the operating system. We will leave it to you to take the networking class to learn more about that. Similarly, graphic devices are particularly important. Take the graphic course to expand your knowledge in that direction. Finally, some operating system books talk a great deal about security. We will do so in the sense that the operating system must provide protection between running programs and give users the ability to protect their file. But we won't delve into deeper security issues that one might find in a security course. However, there are many important topics that we will cover, including the basics of virtualization of the CPU and memory, concurrency, and persistence via device and file system. Important topics that basic of virtualization of CPU and memory. Right. I know about virtual memory, but I didn't realize the virtual CPU. Okay. And then concurrency and persistence via device and file system. Hello, Appa. Kanpur, did you realize that we might have different time zone? And I just woke up, Okay, and then don't worry, well, there is a lot of ground to cover. Most of it is quite cool. And at the end of the road, you'll have new appreciation for how computer systems really work. Now get to work. Tolerating file system mistake with NVFS. A fun paper about using multiple file system at once. Oh, multiple file system at once to tolerate a mistake in any one of them. The evolution of operating system, classic system from batch processing to distributed systems. This essay provides an intro to a wonderful collection of paper, but historically significant system. The evolution of operating system. Let me check. Oh. Fine. Okay. Oh, is this the one? Let's check optional cookies. Okay. When someone provides the PDF, let me check. Let me put this in the chat. Let's take enough night in India. Well, you should go to sleep then. I mean, I just woke up, Updates time sharing system for the PTP-10. Then has much of the machinery found in modern operating system. Motivated to see how much innovation was already in place in the early 1970s. Page time sharing system. Oh, the mythical man mode. A classic text on software engineering. Well, what to read? Okay. me check. Man, mod. Oh, okay, let's try. Wait, if this hyper fail, let me check. Like really? Every scraper fail. You know what? Let's just use this. The mythical man. Okay, this is the one. The essay on software engineering. Now let me put this in the chat. Because anyone wants to check this out. Okay, and then Computer System of Programmer's Perspective. Okay. Another great intro to how computer system work has a little bit of overlap with this book. So if you like, you can skip the last few chapters of that book or simply read them to get a different perspective on some of the same material. After all, one good way to build up your own knowledge is to hear as many other perspectives as possible and then develop your own opinion and thought on the matter. You know, by thinking the lost art of the modern world, the thinking process. The China Manifesto, okay? A huge part of Linux success was not the presence of an excellent compiler, GCC, and other relevant piece of open software, thanks to the genuine effort headed by Stallman. Stallman is visionary. Stallman is a visionary when it comes to open source, and this manifesto result is taught as to why. I think, if I remember correctly, Stallman is not really promoting open source. It's more like the free software movement, you know. It can be different from open source. You can read this out if you want to. We copy this to the chat. Electronic to trade. Well, not really, but I want to learn about this stuff. One level storage system. The Atlas pioneered much of what you see in modern system. However, this paper is not the best read. Okay, or to only read one, you make me try. Story perspective below this one. A history perspective. nice piece of history on the early development of computer system and the pioneer effort of the Atlas. Of course, one could go back and read the Atlas paper themselves, but this paper provides a great overview and adds some historical perspective. The multi-system before the Unix one, an examination of its structure, an overview of multics, so many good ideas, and yet it was over-designed system, shooting for too much, and thus never really worked. A classic example of what Fred Brooks would call the second system effect. Introduction to computer system from bits and gates to C and beyond. Okay, this is another book. One of our favorite intro to computing system books. Start at transistor and get you all the way up to C. The material is particularly great. Okay. The unique time sharing system. Great summary of Unix readiness. It was taking over the world of computing by the people who wrote it. Oh, right. Dennis Ritchie and Ken Thompson. SDS 940 time sharing system. Yes, a technical manual was the best we could find. But it is fascinating to read this old system document and see how much was already in place in the late 1960s. One of the minds behind the Berkeley time-sharing system, which eventually becomes SDS system, was Butler Thompson, who later won a Turing Award for his contributions in system membrane operating system support for restatable file system. Interesting. Restatable file system. The great thing about writing your own class notes, you can advertise. Okay, so this is advertise your own research. But this paper is actually pretty neat. When a file system hits a bug and crash, membrane automatically restart it, all without application or the rest of the system being affected. Oh, interesting. Membrane. Okay. Now let's see at the. Yeah, there's this homework, right? Most and eventually all chapters of this book have homework section at the end. Doing this homework is important as it lets you, the reader, gain more experience with the concept present within the chapter. There are two types of homework. The first is based on simulation. A simulation of a computer system is just a simple program that pretends to do some of the interesting part of what a real system does. and then report some output metrics to show how the system behaves. For example, a hard drive simulator might take a series of requests, simulate how long they would take to get service by a hard drive with certain performance characteristics, and then report the average latency of the request. The cool thing about simulations is they let you easily explore how systems behave without the difficulty of running a real system. Okay, so like this one maybe. We have a homework simulation for the fourth chapter, I guess. Okay. Indeed, they even let you create systems that cannot exist in the real world. For example, a hard drive with unimaginably fast performance, and to see the potential impact of future technologies. Of course, simulations are not without their downside. By their very nature, simulations are just approximation of how a real system behaves. If an important aspect of real-world behavior is omitted, the simulation will report bad result. Is omitted. Okay. If an important aspect of real world is omitted, okay, it is just approximation of how a real system behaves. The result from a simulation should always be treated with some suspicion. In the end, how a system behaves in the real world is what matters. How a system behaves in the real world is what matters. The second type of homework requires interaction with real-world code. The second type of homework requires interaction with real-world code. Some of these homework are measurement focused, whereas others just require some small-scale development and experimentation. Okay, both are just small forays into the larger world you should be getting into. It is how to write system code in C on Unix-based system. Indeed, larger scale projects which go beyond this homework are needed to push you in this direction. Small forays. What is forays? Let me check. Oh, okay. Just small forays into a letter what you should be getting into. It is how to write system code in C on Unix-based system. Indeed, large-scale projects which go beyond this homework are needed to push you in this direction. Thus, beyond just doing homework, we strongly recommend you to project to solidify your system skill. Okay, let me copy this. We can check this. Right. This is. I already put this in the description if you want to take a look, or I can put this in the chat too. Okay, see you next time. Apai Kanpur. Have a nice sleep. Bro, start using Emacs, otherwise the auto will get mad. Well, let the author get mad then. I mean, it's just text editor. Just use whatever you want. Okay, to do these homeworks, you likely have to be on a Unix-based machine, running either Linux, Mac OS, or some similar system. It should also have a C compiler installed, like GCC, as well as Python. Are we gonna use Python too? Okay, interesting. You should also know how to edit code in Real Code Editor. Real Code Editor, yeah, of some kind. Okay. We already read the introduction. Okay. Now let's go to the next chapter, which is the dialogue. Okay. We are going into dialogue first. Part 1, visualization. Where is it? Okay. Here it is. A dialogue on visualization. And thus we reach the first of our 3 pieces on operating system. It is virtualization. Okay. The first piece. Okay. But what is virtualization? Oh, noble professor. Imagine we have a page. A page? What? Yes, a page. Let us call that the physical page. Okay. But we have many eaters who would like to eat this page. Okay. What we would like to present to each eaters is their own page, so that they can be happy. Okay. We call the page we give eaters virtual page. I mean, I'm not sure if someone will be happy with the virtual page, right? So that they can be happy. Yeah, if I got virtual page rather than the physical page, I am not sure if I can eat that. Anyway, we somehow create many of these virtual bits out of the one physical bits. And the important thing in this illusion, we somehow get many of these virtual bits out of the one physical bits. Okay. In this illusion, it looks to its ether like they have a physical bits, but in reality they don't. Right? So this is the illusion. So you are sharing the bits, but you don't even know it. Right, exactly. But there is only one bit. Yes, and well, if I was sharing a bit with somebody else, I think I would notice. Yes, good point. But that is the thing with many ethers. Most of the time, they are napping or doing something else, and thus you can snatch that bit away and give it to someone else for a while. So, okay, we snatch those bits and give it to someone else for a while. And thus we create the illusion of many virtual bits. One bit for each person. Sounds like a bad campaign slogan. Okay. You're talking about computers, right, Professor? Professor. Young grasshopper. You wish to have a more concrete example. Good idea. Let us take the most basic of resources, the CPU. Assume there is one physical CPU in the system. Assume there is one physical CPU in the system. Now there are often 2 or 4 or more CPU in the system. Okay. What virtualization does is take that single CPU and make it look like many virtual CPUs to the application running on the system. Many CPUs, many virtual CPUs to the application running on the system. Thus, while each application thinks it has its own CPU to use, there is really only one. And thus, the operating system has created a beautiful illusion. It has virtualized the CPU. Wow, that sounds like magic. Tell me more. How does that work? In time, young student, in good time. Sounds like you are ready to begin. Well, I am. Well, sort of. I must admit, I'm a little worried you are going to start talking about bitches again. Don't worry too much. I don't even like bitch. And thus we begin. Alright. We're going into the process. This one. The abstraction, the process. Okay. In this chapter, we discuss one of the most fundamental abstraction that the operating system provides to user, the process. Okay, fundamental abstraction. Okay, the definition of a process informally is quite simple. It is a running program. The program itself is a lifeless thing. It just sits there on the disk. Oh, a bunch of instruction and maybe some static data, okay, waiting to spring into action. Okay, the program itself, okay, is a lifeless thing. It just sits there on the disk. A bunch of instruction and maybe some static data waiting to spring into action. It is the operating system that takes these bytes and get them running, transforming the program into something useful. It turns out that one often wants to run more than one program at once. One often wants to run more than one program at once. For example, consider your desktop or laptop where you might like to run a web browser, mail program, a game, a music player, and so forth. In fact, a typical system may be seemingly running tens or even hundreds of processes at the same time. Right, there is this background process in the operating system that we might not notice, but it is there. Doing so makes the system easy to use, as one never need to be concerned with whether a CPU is available. One simply runs program. Hence our challenge. The crux of the problem: how to provide the illusion of many CPUs. Although there are only a few physical CPU available, how can the operating system provide the illusion of nearly endless supply of said CPUs? The operating system creates this illusion by virtualizing the CPU, by running one process, then stop it at running another, and so forth. The OS can promote the illusion that many virtual CPUs exist when in fact there is only one physical CPU or a few. This basic technique known as time sharing of the CPU. Allow users to run as many concurrent processes as they would like. The potential cost is performance, as each will run more slowly if the CPU must be shared. Wait a minute, let me check in here. I kind of forgot. Okay. Okay. I mean, in this one, I kind of, what is it called? Maybe we are answering this question in this paragraph. Maybe. But in this one, is just maybe just an extra information. Maybe. Okay, let me take notes. We'll got editor. Yeah. Other than Emacs, they are not the real code editor. Okay, let me check. How to provide the illusion minute of mini CPUs. The operating system create illusion of mini CPU by virtualizing wait a minute. Okay, virtualizing the CPU, then swapping it time sharing of the CPU. As many time sharing of the CPU. How to explain this time sharing? And then basic technique. Known as time sharing. The CPU is basically running one process. And then stopping it. Switching from one process to another. To another process. The potential process running one process, then stopping it and running another, and so forth. The process can promote illusion that many virtual CPU exist, when in fact there is only one physical CPU. Maybe something like running one process, and then stopping it. And another process, and so forth. So that the operating system create an illusion that many virtual CPU exist, even though when in fact there is only one physical CPU. Only one physical CPU. time sharing. The potential cost is performance, as it will run more slowly if the CPU must be shared. Okay. The implementation virtualization of the CPU and to implement virtualization of the CPU and to implement it well, the operating system will need both some low-level machinery and some high-level intelligence. We call the low-level machinery mechanism. Okay. Mechanism are low-level methods or protocols that implement a needed piece of functionality. For example, we will learn later how to implement a context. Mechanism are low-level methods or protocols that implement a needed piece of functionality. For example, we will learn later how to implement a context switch. Okay. So context switching. Let me read this first. Continuing this. We will learn later how to implement a context switch, which gives the operating system the ability to stop running one program, and start another on a given GPU. Okay. On a given GPU. This time sharing mechanism is employed by all modern operating systems. On top of this mechanism resides some of the intelligence in the operating system in the form of policies. Okay. Policies are algorithm for making some kind of decision within the operating system. For example, given a number of possible programs to run on a CPU, which program should the OS run? Right. We're having all of this program. Which program should the operating system run first? Maybe some kind of like order or requirement, maybe. We will see. A scheduling policy in operating system will make this decision, likely using historical information. Which program has run more over the last minute? Which program has run more over the last minute? Workload knowledge, what type of program are run, and performance metric. Is the system optimizing for interactive performance or throughput to make its decision? Okay, so we have a mechanism and intelligence. Mechanism a low-level method or protocol that implements a needed piece of functionality. This is the low-level methods or protocol for some sort of functionality. And then we have policies. An algorithm for making some kind of decision within the system. Let me take note of that first. implement virtualization session of the CPU. The CPU and to implement it well, the operating system will need both some low-level machinery okay, and some low-level machinery with is called mechanism. And some high-level intelligence. Called policies. Mechanism are low-level method or protocol. Low-level that implement needed piece of functionality. I'm taking note of this definition. Context switch. This time sharing mechanism is employed by all modern operating systems. Policies are algorithms for making some kind of decision. Making some kind of decision. Decision within Alright. A scheduling policy in the operating system will make this decision, likely using historical information, sample which program is run more over the last minute, workload knowledge, what type of programs are run, and performance metric. Is the system optimizing for interactive performance or throughput to make its decision? Okay. The abstract process. Wait. Let me check this first. Use time sharing and space sharing. Okay, let me. Time sharing is a basic technique used by an operating system to share a resource by allowing the resource to be used for a little while by one entity and then a little while by another, and so forth. The resource in question, the CPU or a network link, can be shared by many. The counterpart of time sharing is space sharing, where a resource is divided in space among those who wish to use it. This space is naturally a space-shared resource. Once a block is assigned to a file, it is normally not assigned to another file until the user deletes the original file. Okay, let me take notes. Time sharing. Wait a minute. For a little while by one entity. basic technique use by an operating system to share a resource. Oh, is this why? And I said, the Unix, this one, with the paper called Unix time sharing system. Oh, okay, interesting. To share a resource. By allowing use for a little while. By one entity. And then a little while by another. By another and so forth. And so forth. The resource in question like CPU, locally, can be shared by many. counterpart of time sharing is space sharing. What is counterpart again? Just to make sure. Okay. Space sharing. Space sharing is a technique space sharing is writing system to share when a resource is to fight in space among those who wish to use it. To fight to fight space among those who wish to use it. For example, a file It's normally not. Not assigned. Another file until okay. Does this book have Austin in the title? Yes. This is the book operating system to easy pieces. My university used this exact same book when I took operating system. Oh, okay. Yeah, this is the book that we are using currently. Alright. The abstraction of process. Okay, so I guess that's it for now. We will continue this on the next session. Okay, thank you for watching and see you next time. Bye bye.